Good evening, dear night traveler. As the room grows quiet and your breathing finds an easy rhythm, let the mattress meet you kindly and let the long day drift to the edges. Tonight, we'll wander toward the center of our Milky Way to a hidden heart called Sagittarius A, asterisk, the black hole that anchors our galaxy. For a long time, it was a rumor wrapped in starlight. Now, after years of patient listening and light stitched together from telescopes around the Earth, we finally have a gentle sense of how big it truly is. There's no need to strain for details. I'll keep the pace unhurried, a soft lantern of facts moving through the dark. If a number appears, it will float by like a firefly there to notice, not to chase. If these calm wanderings bring you rest, a quiet tap on like and subscribe helps other sleepy minds find their way here, too. For now, close your eyes if you'd like, and let the galaxy's center hum softly at the edge of your dreams. We'll begin where gravity becomes a lullaby, hidden behind soft lanes of dust and a crowded city of stars. The Milky Way keeps a quiet secret at its center, an object our eyes cannot see, yet heavy enough to steady the whole spiral. Astronomers call it Sagittarius A asterisk, a supermassive black hole with the mass of millions of suns. It isn't the kind that shouts like a faraway quasar. It keeps its voice low, more a steady hum than a blaze. Under that hush lives a weather of extremes, magnetic fields wound tight, gravity so strong that straight paths curl, matter warmed until it forgets what it used to be. This is a calm walk through how we found it, how we learned to picture something that refuses to shine, and what this hidden anchor has already taught us about how the universe holds together. For a long time, the center was a rumor. Early sky watchers could trace the wandering of planets and collect maps of familiar constellations. But when their lenses turned toward Sagittarius, the view turned muddy. Not a wall you could touch more, a curtain made of star-crowded light, stitched with gas and dust. Vision loves contrast. The central region is all overlap. The closer they looked with visible light, the less their instruments could separate one gleam from another. The place we now call the galactic bulge is one of the busiest neighborhoods in our galaxy. From Earth, it swells like the brightest stretch of the Milky Way's river of light, the summer band that drifts from horizon to horizon. Hundreds of billions of stars gather there. Between them float tiny grains, soot-rich carbon, silicate shards, motes kissed with ice debris from dying stars sent back into circulation. Those grains, small as smoke, are excellent at stealing visible light. They scatter it, sip it, turn a broad glow into streaks and shadows, like charcoal brushed across glass. Where the dust runs thickest, starlight dims by orders of magnitude. To our eyes, the heart becomes a silhouette. The bulge itself deepens the puzzle, while the spiral disk stretches flat and wide like a luminous harbor. The bulge rises round and dense. Stars live closer together, shining in all directions at once. Their light overlaps into a continuous shimmer, as if you were staring at sunlit water from far above, movement everywhere. No single wave to isolate. Signals pile atop signals. The melody is present, but the notes blur. That blur tempted people to fill the center with guesses. Some wondered whether the Milky Way even needed a heart. If the galaxy were only a gathering of loose associations, stars, clusters, clouds, perhaps it didn't rotate around anything in particular. Maps drawn by care and patience captured the arcs of nearby arms, counted local clusters, and still the core stayed uncertain. The limits were not only in imagination, They lived in the kind of light our tools could catch. For most of human looking, telescopes used the same narrow band our eyes do. Visible light, a slim slice of the electromagnetic spectrum, useful, colorful, precise, but easily stopped by dust. A single cloud can turn a lantern into darkness. The galaxy's midplane is not a single cloud. It is a layered quilt of them. Because of that blindfold, some early thinkers placed the sun near the center. When they swept the sky and counted stars, the numbers seemed broadly similar in many directions, as if we lived on a favored street. The trick was dust again. It erased the far districts in certain lines of sight, forging the illusion that our corner was as central as any. William Herschel, careful and ingenious, tried to infer the Milky Way's shape by star counts in the late 1700s. Without a way to correct for dimming by interstellar grains, his senses leaned wherever the dust thinned, a map shaped by the fog it could not see. Patience and new senses loosened the knot. In the 20th century, scientists began to work with kinds of light that slip past dust. Infrared waves, with their longer reach, move like low notes under a closed door. Radio waves, longer still, stroll by dust grains, too small to scatter them much. These lights are invisible to our eyes, but not to instruments tuned to them. Build the right receiver, and a dark patch becomes a choir. Infrared telescopes climbed mountains to escape Earth's own warm glow and the blur of water vapor. Later, some rode rockets beyond weather and air. When they looked toward the bulge, the star fields opened. Hidden clusters flashed out, rivers of gas uncoiled, lit from within. The heart stopped looking empty and started looking lively. A key turn came from work that did not begin as astronomy. In the early 1930 seconds, Carl Jansky, at Bell Telephone Laboratories, was asked to track down a stubborn hiss that spoiled long-distance radio calls. He built a rotating antenna, a wooden and wire contraption on wheels tuned to roughly 20.5 megahertz radio waves with a wavelength around 15 meters. He listened for months. Nearby, thunderstorms announced themselves with sharp cracks. Distant lightning murmured, but a third kind of noise rose and fell with a rhythm that slipped by about 4 minutes earlier each day. That little drift marks the difference between the sun's day and the star's day solar time versus sidereal time. The source wasn't weather, and it wasn't the Sunday, it was the sky itself. When Jansky traced the direction, the strongest signal came from the arch of the Milky Way, and, more particularly, from the crowded deep of Sagittarius. He had logged the first confirmed radio waves from beyond the solar system. An engineer, following noise, had opened a new sense for the species. The world did not pivot at once. Optical astronomy had the momentum of centuries. Jansky's antenna was dismantled. The seed, however, was planted. Groth Reber, a radio engineer with a taste for practical adventure, read Jansky's report and decided to keep listening. He built a 9-meter parabolic dish in his backyard, a silver bowl leaning into the sky. Night after night, he swept the heavens and stitched a radio map. The Milky Way glowed bright in that new light, with a rounded swell towards Sagittarius. Where visible light was blocked, radio light flowed through, sketching a center that had been invisible to ordinary sight. Through the 1,940 seconds and 1,950 seconds, listening multiplied. Wartime radar skills fed peacetime instruments. Dishes grew larger, receivers quieter, techniques sharper. Arrays of antennas learned to act together, a method called interferometry that mimics a single instrument as wide as the distance between dishes. This widened the eye without building an impossible mirror. Radio astronomers traced supernova remnants like smoke rings from old explosions, followed hydrogen gas by its faint 21-centimeter line, and charted spiral arms the way cartographers trace coastlines. Regions that looked dull to the eye turned bright at longer wavelengths, proof that the universe uses many kinds of light, each with its own messages. The center, once a rumor, began to feel particular. Infrared cameras peered through the worst of the dust and found stars moving on tightly bent paths near an unseen mass. Radio receivers noticed knots and filaments, arcs and threads, structures drawn by magnetic fields and wind-blown gas. Somewhere in that crowded thicket, a point-like radio source spoke clearly. Compact in size, yet strong in signal, it did not stretch across the sky. It held its shape. It flickered only a little, like weather close to home rather than storms far away. That compact steadiness suggested something both tiny in extent and immense in influence. To reach such delicacy, observers learned to subtract the planet's own voice from the data. The atmosphere ripples, the ground radiates, human machines hum and click. Careful calibration turns mess into music. Antennas were spaced across deserts and mountaintops, then linked with precise clocks, first crystal, then rubidium and cesium standards, so recordings made far apart could later be rejoined, wave by wave, as if Earth itself were a lens. This very long baseline interferometry made it possible to measure not only direction, but apparent size, how small the emitting region must be to avoid being blurred by the instrument's resolution. Even before images grew sharp, the motions of nearby stars began to testify. In the central few light years, stars moved like birds near a weather eye. Sudden accelerations, tight arcs, periods measured in years rather than millennia. To bend a star's path so swiftly requires mass concentrated in a volume so small that alternatives thin out. A cluster of ordinary stars would be too big and too bright. It would reveal itself and disperse. A nest of neutron stars or stellar mass black holes would jostle, merge, and glow in ways we would notice. The simplest, cleanest explanation was a deep well in space-time, a black hole with millions of solar masses. Notice how gently the case builds. Nothing in these observations asks for fireworks. They ask for quiet patience, instruments tuned to calm bands, the habit of letting numbers lead, while imagination follows at a respectful distance. Each improvement in sensitivity does not shout. It nods, a quieter receiver here, a longer baseline there, a winter of steady air, a summer of clear nights. Pieces collect like dew. Infrared observations added a soft but decisive line of evidence. Dust shines faintly in the infrared, warmed by the stars it hides. Through that glow, astronomers tracked individual stars close to the unseen mass and watched them swing around a point that emitted almost no light at all. One star traced an ellipse, short enough to complete within a single scientific career. Near its closest approach, its speed climbed to thousands of kilometers per second, a supersonic whisper guided by gravity's hand. The mass required for that choreography can be calculated the way one infers a hidden planet from the tug it gives a visible one. The answer kept landing in the same place, millions of suns worth of mass gathered where no luminous object sat. Call it discovery, if you like, though it felt more like a series of clearings. First, the recognition that dust is a filter, not a final darkness. Then, the proof that certain kinds of light pass almost unhindered. Next, the detection of a compact radio source nestled at the core. Alongside it, the patient tracking of stellar orbits, proof by motion, written in loops and speeds rather than in brightness. Finally, techniques sharpened enough to tease shape from the radio glow itself, to measure how small the brightest knot must be and how wide the faint structures around it. Piece by piece, the invisible earned a silhouette. There is comfort in knowing that something so intense can also be so reserved. Sagittarius A times does not blaze, it murmurs. Material that drifts inward may heat and swirl, but much of it misses the narrow door that feeds the whole and continues on. Magnetic fields wind and unwind. The region breathes in slow physics, not quiet because nothing happens, quiet because the happenings balance more than they break. If the galaxy were a living city, this would be the old square at its heart, not empty, not loud, full of eddies and small conversations, governed by a calm gravity that has been there longer than anyone remembers. When the final strands of evidence were woven tight, the idea of a supermassive black hole at the Milky Way's center stopped sounding bold and started sounding obvious. A compact, powerful source sits exactly where the stellar orbits point, a mass so concentrated that alternative stories run out of room, a presence that doesn't need to shine to be known. The dust curtain still hangs, but we've learned to see around it, through it, and, in a way, by means of it, since the dust itself glows at the wavelengths that guide us. The sky didn't change, we changed how we listened. That lesson began decades earlier, when radio telescopes became our careful ears. By the 1,960 seconds, they could hear the galaxy's low music, in detailed deep notes from cold hydrogen, fading echoes of supernova remnants, even whispers from far-off galaxies. Amid that wide chorus, one source kept calling us back to Sagittarius, a strong, compact point of radio light at the Milky Way's heart. It didn't flicker like a temperamental star or spread like a nebula. It held fast, small and stubborn, as if pinned to a needle's tip, hinting at something tiny in size yet immense in pull. Even through the 1,970 seconds, its nature remained a puzzle. The spectrum didn't behave like a known nebula. The shape wasn't the shell of a supernova remnant. The behavior didn't match clusters of ordinary stars. To learn more, astronomers needed a different kind of evidence, the kind that accumulates slowly, the motion of stars circling an unseen center. The core of the Milky Way sits about 26,000 light-years away. Stars there can move at thousands of miles per second, but orbits still take years, sometimes decades, to draw their loops. You cannot rush a dance written in gravity. You set up the instruments, you keep watch, and you let time reveal the curve. That meant learning to see through dust without losing the stars. Infrared light became the gentlest tool for the job, wavelengths longer than red, able to slip past dust grains that easily block visible light. At first, the efforts were humble and inventive. Instruments lofted on high-altitude balloons, telescopes riding in aircraft above the wettest layers of air. Earth's atmosphere swallows a great deal of infrared. To catch what survives, you go higher and drier. So, observatories climbed mountains. Mauna Kea's cold, thin air in Hawaii, the Atacama's desert clarity in Chile. Up there, water vapor thins, heat shimmer calms, and more of the faint warmth from the galactic center reaches the detectors. From those high places came the first crisp hints of what the dust had hidden. Patches that looked empty in visible light turned out to be crowded neighborhoods in the infrared clusters of stars, lanes of warm gas, arcs and knots shaped by magnetic fields. The heart of the Milky Way was alive with motion, not a quiet void, but a tight square, buzzing softly with activity. Even so, the ground has its limits. The Earth glows in the infrared. The atmosphere ripples. Some wavelengths simply cannot be studied cleanly from below. The next step was to take the chill and silence of space itself and use it as an observing room. In 1983, the Infrared Astronomical Satellite mapped the sky in infrared for the first time. It did not linger just on the galactic center, yet its all-sky survey changed the mental map. Swaths of darkness in optical images lit up in infrared, full of newborn stars, warm dust, and mysterious heat sources. A hidden universe stepped forward. 2 decades later, the Spitzer Space Telescope carried that calm work deeper. Its instruments were cooled to very low temperatures, quiet enough to hear faint heat from far across the galaxy. When Spitzer turned toward the core, it saw stars crowding close to a dense, invisible knot, exactly where radio astronomers had long placed the compact source known as Sagittarius A*. From orbit, it provided the broad, sensitive view. From the ground, the next generation of infrared cameras chased sharpness, learning to freeze the atmosphere's shimmer with short exposures and to correct it on the fly using adaptive optics. In Chile, at the European Southern Observatory's Very Large Telescope, Reinhard Genzel's team committed to patient tracking, returning season after season to take the measure of stars near the center. In Hawaii, at the W.M. Keck Observatory, Andrea Gheze's group did the same, bringing equally sharp tools and the same long attention. Adaptive optics turned the atmosphere from a distorting lens into a manageable ripple, reshaping the wave fronts in real time so that the stars near the core could be separated like beads in a crowded strand. Those stars, nicknamed stars, became wayfinders, tiny in the images but decisive in their motion. They looped around a point that refused to shine. One star in particular, S2, became the metronome. Its orbit stretches long and then tightens dramatically, swooping in close to the invisible center before gliding back out. By following S2 for years, both teams could read the mass of whatever it circled, the way you can weigh an unseen dancer by the force they impress on a partner. The results settled with a quiet kind of shock, about 4 million times the mass of the Sun, packed into a region smaller than our solar system. No cluster of ordinary stars could hide in such a small space without lighting the place up. A swarm of neutron stars or small black holes would merge, rattle, and betray themselves. The simplest, cleanest answer held: a supermassive black hole. Infrared astronomy made this possible. Visible light still failed at the core. Dust kept it away. In the infrared, the scene opened. Stars traced elegant arcs. Speeds spiked near closest approach, and gravity wrote its signature, not in brightness, but in motion. Meanwhile, radio observations kept supplying their steady, supporting notes, a compact source with structure on very small scales, filaments of ionized gas, the soft rumor of magnetic fields shaping flows. 2 very different senses agreed on the same location and the same story. Getting there meant learning to remove the world's own voice from the data. Astronomers measured and subtracted the telescope's gentle warmth, the air's restless ripple, the hum of human electronics. They anchored observations to precise timekeeping so that signals could be combined and compared without blur. They built catalogs of reference stars to fix the field, like thumbtacks on a map. Bit by bit, the uncertainty shrank until the orbits stood out cleanly, curves you could draw with a fingertip in the air. What emerged is both fierce and restrained. Material drifting inward near the center can heat to great temperatures, wind into streams and eddies, and yet much of it misses the narrow path that would carry it over the horizon. The black hole at the core does not need to blaze to be known. It instructs by influence. Stars speed up as they round the bend, light red shifts in its deep well, and the dust nearby glows faintly from the neighborhood's warmth. The portrait is not a single snapshot, but a composite of thousands of careful moments, years of steady watching, and the grace of instruments tuned to notice what is easy to miss. There is a soft reassurance in how this conclusion was reached. No grand spectacle, no single night of revelation, just the patience to let orbits close, the humility to trust measurements, and the craft to see in wavelengths our eyes cannot. Where optical maps insisted on a blank, the infrared insisted on a crowd. Where radio maps pointed to a compact heart, the stars themselves agreed by the way they turned. When S2 swung through its closest pass and the calculations clicked into place, the idea of any alternative lost its footing. The numbers, like stones in a path, lined up so neatly that the way forward felt inevitable. What lingers is an intimacy with something unimaginably strong. The Milky Way's center isn't loud, it's steady. It holds the galaxy the way a deep keel steadies a ship, without announcement, by sheer presence. We learn to recognize that presence by what it asks nearby stars to do, by the faint warmth it lends to dust, by the neat compactness of its radio voice. The dust still lies between our eyes and the core invisible light, but we've found gentler ways to look, and under those wavelengths the hidden heart keeps its rhythm, the quiet gravity that shapes a city of stars. That rhythm became trustworthy the slow way, measured star by star, the quiet choreography that revealed the galaxy's heart stands as one of modern astronomy's tender triumphs. With the right instruments, a star's position can be fixed to a fraction of an arcsecond, like sensing the width of a hair from miles away. In a single night, the change is only a rumor. Over years, then decades, the rumor becomes a story you can trace with a fingertip. In the 1,990 seconds, that patience settled into 2 long vigils, one led by Reinhard Genzel from observatories in Chile, the other by Andrea Ghez at UCLA from Mauna Kea in Hawaii. Different hemispheres, different teams, the same soft insistence on measurement, and the same target, veiled by dust, answering in motions too consistent to ignore. Even with infrared detectors, Earth's air kept reaching into the images, stirring the stars until they looked like glints on a shaking pond. To calm that pond, astronomers turned to adaptive optics, a technology that listens to the atmosphere's distortions in real time and gently cancels them. The method begins with a reference light, sometimes a bright star, and often a star made to order, a beam aimed into the mesosphere to tickle sodium atoms about 90 kilometers up so they glow. That artificial star is not the goal, it's a guide. As its returning light ripples through the same restless air as the starlight, Computers read the ripples and instruct a thin, flexible mirror to change shape hundreds of times each second. The mirror's surface breathes and shivers in microscopic ways, bending the incoming wavefronts back towards smoothness. What was once a fuzzy smear tightens into pinpoints. The crowd of the galactic center separates into individuals. With that clarity, the immediate neighborhood of Sagittarius A times became legible. Stars near the core were not meandering. They were moving with purpose, fast enough to feel like whispers, sharpened to a hiss. Some speeds climbed above 5,000 kilometers per second, swift enough, in a cheeky comparison, to cross the Earth-Moon gap in barely more than a minute. The paths bent hard around a point that refused to shine. You could not see the cause directly, but you could see every effect. The breakthrough was not a flash of discovery, but a harvest of returns. One star, labeled S2, emerged as the faithful drummer. Bright enough to follow and close enough to tell a full story, it drew a long ellipse that tightened sharply near the center. 16 years was the time it needed to complete a loop, long in the rhythm of human plans, short in the rhythm of galaxies. Through those years, both groups kept their cadence, logging positions, fitting curves, trimming uncertainties. The ellipse spoke plain gravity, not a push from winds or a shove from neighbors, but a clean, central pull. From any orbit, you can weigh the thing being orbited. You don't need to see the mass itself. You read it from the sweep, how quickly the star turns, how sharply it curves at closest approach, how long it takes to return. The numbers settled with a quiet firmness. The central mass came out around 4 million suns. The space it occupied, inferred from how tightly the orbits tucked in, was smaller than our solar system. That amount of matter crammed into such a small volume leaves very little room for alternatives. A cluster of ordinary stars would light the region like a lantern and would not stay that compact for long. A swarm of dead remnants would produce telltale collisions and radiation. The simple, sturdy conclusion stayed standing after others fell away. A supermassive black hole. The elegance of the case deepened as the dataset grew. More stars were found, some with longer periods, a few with paths that skimmed even closer than S2. Each added its own loop to the notebook. Each loop agreed, as if different instruments were joining a chord already in tune, and nestled within the harmony were faint deviations that mattered. The point of closest approach for S2 did not repeat in exactly the same place. It shifted a little, an advance of the periaps, the kind of precession predicted by Einstein's general relativity, when gravity grows so strong that space-time itself flexes. Timing offsets appeared that Newton's laws alone could not explain. Light from the star dimmed and reddened at exactly the moments when it should, as photons worked their way out of a deeper gravitational well. Where the classical picture ends, the relativistic one takes over, not loudly, but with a series of small, correct nudges. Publication marked milestones on the path without claiming to end it. In 2002, the UCLA team released the first full orbit of S2, a loop sketched with enough fidelity to fix the mass and the distance more tightly than before. In 2008, the Genzel group reported equally precise measurements that landed on the same answer. Independent eyes, independent instruments, the same conclusion. Redundancy can feel unglamorous. Here, it felt like kindness. When two watches keep the same time, you begin to trust the hour. As the 2010 seconds opened out, technique kept refining the view. Positions were pinned to the sky with thousandths of an arcsecond of accuracy, like checking the width of a hair from several kilometers away and getting the same number, night after night. Calibrations grew gentler and more exacting. Better models of how the camera warps the field, better catalogs of reference stars to anchor the frame, better control of how the atmosphere's breath sneaks into the signal. The story did not change under the harsher light of precision. It grew sharper around the edges. All of this unfolded without a direct picture of the black hole itself. What the instruments recorded were the footprints, the dance steps executed by stars obliged to curve around the unseen. Yet those steps were unambiguous. You could lay the predictions of a central, compact mass on top of the data and feel the fit. You could look for ways to make the loops with something else and find those ways narrowing, then closing. Confidence did not come from rhetoric. It came from orbits that closed as they should, from relativistic precession that matched the equations, from redshifts that arrived on cue. The craft behind the scenes mattered as much as the stars on the stage. Teams learned to subtract the telescope's own warmth, which glows at the same wavelengths they hope to study. They learned the personality of their instruments, tiny flexures as temperatures changed, subtle tendencies of detectors to shift scale, slight tilts introduced by optics. They learned to keep immaculate time so that measurements gathered months apart could be compared as if collected in one breath. They learned to treat the air as a moving lens that can be tamed rather than suffered. The result was not only sharper images, but cleaner math, the kind you can trust, with something as bold as weighing an invisible object at the center of a galaxy. What these long watches created is a portrait painted in motion. The subject is not seen, it is inferred with a care that becomes its own kind of seeing. Material near the center heats and whirls. Magnetic fields thread the gas. Most of that gas fails to fall in, slipping past the narrow, inward paths and continuing on. Meanwhile, the stars, old, patient, used to gravity's customs, show exactly where the deepest part of the well lies and how steep its sides are. That's enough to recognize a black hole by touch, the way you recognize a friend in the dark by the way they move. There was a softness to the way certainty arrived. No fireworks, no shouted, reveal only the quiet stacking of clear nights, the click of instruments finding focus, the calm relief of numbers that agree. To ordinary sight, the galactic center stayed hidden, but in infrared, it unfolded like a map creased too long in a pocket. In that glow, the stars left careful signatures, and those signatures weighed the mass that steadies the city of stars. The black hole itself kept its face turned away. The trail of evidence, step by tender step, was enough to know it was there and to feel the contour of its size. That trust was earned the slow way, measured star by star. The quiet choreography that exposed our galaxy's heart became one of modern astronomy's gentlest triumphs. With the right tools, a star's position can be fixed to a tiny fraction of an arcsecond, as if sensing the width of a hair from miles away. In a single night, the change is only a rumor. Across years, then decades, the rumor becomes a line you can trace with a fingertip. In the 1,990 seconds, that patience settled into 2 long vigils. Reinhard Genzel's team returning season after season from Chile, and Andrea Gez's team keeping watch from Mauna Kea in Hawaii. Different hemispheres, different crews, the same soft insistence on measurement, and the same dust-veiled target answering in motions too consistent to ignore. Even with infrared detectors, Earth's air kept reaching into the images, stirring the stars until they looked like glints on a shaking pond. To calm that pond, astronomers turned to adaptive optics, a technology that listens to the atmosphere's distortions in real time and gently cancels them. The method begins with a reference light, sometimes a bright star, and often a star made to order, a beam aimed into the mesosphere to tickle sodium atoms about 90 kilometers up so they glow. That artificial star is not the goal, it's a guide. As its returning light ripples through the same restless air as the starlight, computers read the ripples and instruct a thin, flexible mirror to change shape hundreds of times each second. The mirror's surface breathes and shivers in microscopic ways, bending the incoming wavefronts back toward smoothness. What was once a fuzzy smear tightens into pinpoints. The crowd of the galactic center separates into individuals. With that clarity, the immediate neighborhood of Sagittarius A times became legible. Stars near the core were not meandering. They were moving with purpose, fast enough to feel like whispers sharpened to a hiss. Some speeds climbed above 5,000 kilometers per second, swift enough, in a cheeky comparison, to cross the Earth-Moon gap in barely more than a minute. The paths bent hard around a point that refused to shine. You could not see the cause directly, but you could see every effect. The breakthrough was not a flash of discovery, but a harvest of returns. One star, labeled S2, emerged as the faithful drummer, bright enough to follow and close enough to tell a full story. It drew a long ellipse that tightened sharply near the center. 16 years was the time it needed to complete a loop, long in the rhythm of human plans, short in the rhythm of galaxies. Through those years, both groups kept their cadence, logging positions, fitting curves, trimming uncertainties. The ellipse spoke plain gravity, not a push from winds or a shove from neighbors, but a clean, central pull. From any orbit, you can weigh the thing being orbited. You don't need to see the mass itself. You read it from the sweep, how quickly the star turns, how sharply it curves at closest approach, how long it takes to return. The numbers settled with a quiet firmness. The central mass came out around 4 million suns. The space it occupied, inferred from how tightly the orbits tucked in, was smaller than our solar system. That amount of matter, crammed into such a small volume, leaves very little room for alternatives. A cluster of ordinary stars would light the region like a lantern and would not stay that compact for long. A swarm of dead remnants would produce telltale collisions and radiation. The simple, sturdy conclusion stayed standing after others fell away. A supermassive black hole. The elegance of the case deepened as the data set grew. More stars were found, some with longer periods, a few with paths that skimmed even closer than S2. Each added its own loop to the notebook. Each loop agreed, as if different instruments were joining a chord already in tune, and nestled within the harmony were faint deviations that mattered. The point of closest approach for S2 did not repeat in exactly the same place. It shifted a little, an advance of the periapse, the kind of precession predicted by Einstein's general relativity, when gravity grows so strong that space-time itself flexes. Timing offsets appeared that Newton's laws alone could not explain. Light from the star dimmed and reddened at exactly the moments when it should, as photons worked their way out of a deeper gravitational well. Where the classical picture ends, the relativistic one takes over, not loudly, but with a series of small, correct nudges. Publication marked milestones on the path without claiming to end it. In 2002, the UCLA team released the first full orbit of S2, a loop sketched with enough fidelity to fix the mass and the distance more tightly than before. In 2008, the Genzo group reported equally precise measurements that landed on the same answer. Independent eyes, independent instruments, the same conclusion. Redundancy can feel unglamorous. Here, it felt like kindness. When two watches keep the same time, you begin to trust the hour. As the 2010 seconds opened out, technique kept refining the view. Positions were pinned to the sky with thousandths of an arcsecond of accuracy, like checking the width of a hair from several kilometers away and getting the same number, night after night. Calibrations grew gentler and more exacting. Better models of how the camera warps the field, better catalogs of reference stars to anchor the frame, better control of how the atmosphere's breath sneaks into the signal. The story did not change under the harsher light of precision. It grew sharper around the edges. All of this unfolded without a direct picture of the black hole itself. What the instruments recorded were the footprints, the dance steps executed by stars obliged to curve around the unseen. Yet those steps were unambiguous. You could lay the predictions of a central, compact mass on top of the data and feel the fit. You could look for ways to make the loops with something else and find those ways narrowing, then closing. Confidence did not come from rhetoric. It came from orbits that closed as they should, from relativistic precession that matched the equations, from redshifts that arrived on cue. The craft behind the scenes mattered as much as the stars on the stage. Teams learned to subtract the telescope's own warmth, which glows at the same wavelengths they hope to study. They learned the personality of their instruments, tiny flexures as temperatures changed, subtle tendencies of detectors to shift scale, slight tilts introduced by optics. They learned to keep immaculate time so that measurements gathered months apart could be compared as if collected in one breath. They learned to treat the air as a moving lens that can be tamed rather than suffered. The result was not only sharper images, but cleaner math, the kind you can trust with something as bold as weighing an invisible object at the center of a galaxy. What these long watches created is a portrait painted in motion. The subject is not seen. It is inferred with a care that becomes its own kind of seeing. Material near the center heats and whirls. Magnetic fields thread the gas. Most of that gas fails to fall in, slipping past the narrow, inward paths and continuing on. Meanwhile, the star's old, patient, used to gravity's customs show exactly where the deepest part of the well lies and how steep its sides are. That's enough to recognize a black hole by touch, the way you recognize a friend in the dark by the way they move. Certainty arrived softly. No fireworks, no shouted reveal, just the quiet stacking of clear nights, the click of instruments finding focus, the calm relief of numbers that agree. To ordinary sight, the galactic center stayed hidden, but in infrared, it unfolded like a map creased too long in a pocket. In that glow, the stars left careful signatures, and those signatures weighed the mass that steadies the city of stars. The black hole itself kept its face turned away. Step by step, the evidence was enough to know it was there and to feel the contour of its size. What those careful weights hinted at close to home, the wider sky soon echoed. Astronomers once treated supermassive black holes as rare curiosities, yet the pattern kept repeating like a soft refrain. Wherever a galaxy gathers its light, a heavy heart waits at the center. Grand spirals, smooth ellipticals, even unsettled irregulars. Again and again the signs pointed to a compact, massive anchor. The first clues came from cores that blazed far too brightly for stars alone. Those energetic centers' active galactic nuclei poured out more light than whole clusters could muster. The simplest, most patient reading was matter falling inward, heating and glowing as it spiraled down to feed a central giant. The same logic illuminated quasars, beacons from billions of light years away, now understood to burn on black holes weighing millions to billions of suns. Once the right tools existed, the search broadened to quieter galaxies. Even where the core looked dim and calm, the motions of nearby stars and gas betrayed a deep pull. Sometimes the giant slept, hardly eating at all, yet its gravity still shaped the neighborhood. It soon became harder to find a galaxy without a central heavyweight than to find one with it. The question changed keys, not whether our galaxy harbored such an object, but why almost every galaxy seems to. One gentle answer is that black holes and galaxies were born together, each shaping the other's growth. In the early universe, some clouds may have collapsed directly into massive black holes rather than breaking into ordinary stars. Those seeds could grow by drawing in gas and dust, and by merging with other black holes as young galaxies collided. Another possible beginning starts with the first stars, giants far larger than any common today, burning briefly and ending in collapses that left hefty cores. However they began, those seeds had the room and the time to become the anchors we see now. A clue to that shared history lives in a quiet correlation. The mass of a galaxy's central black hole tends to track the mass of its bulge, the dense central hive of old stars. Big bulges pair with big black holes, smaller bulges pair with smaller ones, and the line between them is surprisingly neat across great ranges. That tidiness hints at feedback, a two-way conversation. When the black hole feeds greedily, it can launch winds and jets that push gas outward, thinning the raw material for new stars and slowing the galaxy's growth. When the galaxy is rich in gas and forms many stars, some of that material eventually sinks toward the middle, delivering fresh fuel to the black hole. Growth is not a straight climb, but a duet, sometimes a lullaby, sometimes a storm played out over billions of years. The timeline complicates the melody. Astronomers have found quasars shining when the universe was less than 1 billion years old, powered by black holes already weighing 1 billion suns or more. To grow that big so quickly requires either unusually fast feeding, frequent mergers, an early head start with massive seeds, or some mixture of all three. The details remain an open, careful conversation, but the existence of those youthful giants tells us that the universe can build big, and it can do so swiftly when conditions allow. Against that vast scale, Sagittarius A times looks modest, a family-sized heavyweight. It sits near 4 million solar masses, enormous by human standards, humble compared with the titans. In the giant elliptical galaxy M87, the central black hole carries several billion solar masses and was the one whose shadow was famously sketched in 2019 by a planet-spanning collaboration. Its event horizon could hold our solar system well inside. Even M87's object is not the upper limit. In the sprawling heart of Holmberg 15A, estimates reach into the tens of billions of suns. And in the distant quasar known as Ton 618, the likely mass is on the order of 40 billion suns. a figure that turns comparisons into quiet astonishment. If Sagittarius A times is a mountain, Ton 618 is a continent. Scale, however, doesn't automatically mean menace. The reach of gravity feels overwhelming only close in. Farther out, a black hole's pull behaves like any other mass of the same size. Steady, predictable. What changes from place to place is the supply line. Some environments are rich in gas and dust. Collisions and inflows heap fuel onto the center, and the black hole answers with bright accretion disks and sometimes with jets that spear into intergalactic space. Other environments are lean, and the center idles, sipping rather than feasting. Sagittarius A times lives in the second kind of neighborhood. It nibbles, flaring now and then in radio and X-rays when a knot of gas wanders too close, but spends most nights quiet to casual eyes. A quasar like Ton 618, by contrast, is in full blaze, its accretion disk outshining entire galaxies and helping it grow larger still. The past may have held a different tempo. Signs suggest that our galactic center once flared more brightly than it does now. The sky near the Milky Way shows great lobes of high-energy emission billowing shapes known as Fermi bubbles that could be leftovers from a more active phase, like embers in a long-cooled fire. If Sagittarius A times had a feeding spell a few million years ago, it might have lit up the galaxy's midsection, driving outflows that sculpted the halo and left quiet signatures for us to find much later. Spin adds another layer to the portrait. A black hole's rotation can shape how matter falls in and how energy escapes. Fast spin tightens the innermost stable orbits, stirs magnetic fields, and can help power jets that streak away at near light speed. The exact spin of Sagittarius A times is still being pinned down carefully, while giants like the one in M87 appear to whirl close to the limits allowed by physics. That swift rotation does not make them wild. It makes them efficient cosmic mixers that can turn in falling matter and magnetic fields into beams and winds. Growth can come by many paths. Sagittarius A times likely started smaller and put on mass by drawing in gas and dust, swallowing the occasional unlucky star, and merging with other black holes brought in during minor galactic collisions. The Milky Way bears the scars of past mergers. Each incoming dwarf galaxy may have carried its own compact anchor, which would slowly sink toward the center and combine. Over billions of years, that is enough to build a steady heavyweight, even without long quasar phases. For the true giants Holmberg 15A center, Ton 618 seeds probably began larger, the fueling heavier, and the mergers more frequent. Their host environments are different too. Galaxy clusters where traffic is heavy and interactions common, places where a central black hole can dine often and richly. Looking ahead, our own center will not stay the same size forever. The Milky Way and the Andromeda Galaxy are on course to meet in a few billion years, and their central black holes will almost certainly spiral together. The result will be a heavier core for the merged galaxy and a gravitational wave ripple sent through space-time, a quiet, immense bell rung once across the dark. Even smaller feasts, a stream of gas here, a disrupted star there, will add ounces and pounds on cosmic scales, slowly changing the ledger of mass. These comparisons remind us that black hole describes a family, not a single personality. Sagittarius A times sits in a relatively calm spiral, a mixed neighborhood of old stars, new stars, and moderate gas. Ton 618 blazes in the company of a quasar, a lighthouse seen from the other side of time. M87 anchors a massive elliptical and launches a jet that paints the space around it. The same physics governs them all, but the settings decide which notes are loud and which are barely a hum. What threads through every case is the intimacy between a galaxy and its center. The correlation between black hole mass and bulge mass suggests that the core is not an afterthought but part of the blueprint. When the center feeds hard, it can change the weather of the whole system, driving winds that rearrange gas, shaping where and when stars are born. When the supply wanes, the galaxy can catch its breath. Across eons, that back and forth writes a slow history. Star formation, outflow, quiet, renewal. The black hole is not the galaxy, but it helps set the tempo. For us, the scale differences can be difficult to hold in mind, so gentle anchors help. Imagine the event horizon, the surface beyond which light cannot return, as a kind of boundary that scales with mass. Sagittarius A *''s horizon would take on the order of tens of seconds for light to cross. Ton 618's would demand days. Both are invisible in ordinary light. Both curve space the way a heavy stone curves a stretched sheet. Both grow when they are fed and wait patiently when they are not. The difference is simply how much fuel the neighborhood provides and how efficiently the spin and magnetic fields can help turn that fuel into light and wind. All of this makes our galactic center feel both ordinary and special. Ordinary, because it fits a pattern seen almost everywhere we look. Special, because it is ours to study in detail, close enough for individual stars to become characters rather than statistics. In its presence, there is no menace, only the lesson that gravity can be strong and still a deep keel rather than a storm. We know it not by what it shows in visible light, but by what it asks its neighbors to do, and by the faint warmth of dust nearby. They leave us with a quiet sense of proportion. Some black holes glow like cities, others rest like small towns at midnight. Some centers eat fast and grow towers of light. Others sip and keep a low profile. For now, Sagittarius A times lives in the latter mood, a modest heavyweight in a calm season, more felt than seen. The universe doesn't insist on spectacle. Often it prefers persistence and balance. In that gentler register, our center steadies the Milky Way, while louder giants conduct their noisy business far away. And for all that weight, the voice at our core stays soft. Sagittarius A times sits like a stone in a river, letting most of the flow slide past. Black holes don't tire or mellow with age. Whenever matter strays close enough, gravity writes the ending. What shifts from era to era is the supply. Around our black hole, the pantry is sparse. Gas and dust are thin compared with the rich larders in active galaxies. Threads that wander inward are warmed, stirred, and often tossed back out before they can thread the narrow path to the horizon. They swirl, shed a little energy, and ride outward again on small winds and turbulence. Only a trickle makes it to the place where falling becomes forever. A small meal means a dim table. In radio, infrared, and X-rays, the glow is present, but modest, like embers, not a bonfire. By contrast, a quasar feasts loudly, blasting more light than whole galaxies of stars. If our own center suddenly began eating at that rate, the Milky Way would wear a new jewel, a luminous core, rivaling bright stars, and, at peaks, edging toward daylight visibility. It's a captivating thought and a slightly unsettling one, because it would redraw the familiar face of our sky. This quiet helps explain why the heart stayed secret for so long. A loud, flaring nucleus would have announced itself early in the radio and X-ray era. Instead, the first detections were whispers that demanded years of careful listening to confirm. 26,000 light-years is near enough to measure motions with patience, yet far enough that a muted center can hide in plain sight. Only with the right wavelengths and the right steadiness did the outline sharpen into certainty. Silence, in this case, carries news. The calm suggests a central neighborhood that has been relatively peaceful for millions of years. Elsewhere, astronomers see galaxies with mile-high signatures of violence, jets lancing thousands of light-years into space, lobes of radio emission ballooning outward, shock waves heating gas like the aftermath of distant storms. In the Milky Way, the most dramatic hints of past fireworks are the great Fermi bubbles, soft, rounded expanses of high-energy light rising above and below the plane. They look like the afterglow of a busier season. If that reading is right, our center is between courses, taking its time. There is no guarantee the hush will last. The inner few light-years are braided with gas streams and crowded with stars, and gravity's choreography ensures that now and then something will wander too near. When that happens, the dimness flickers. Observers have recorded brief outbursts, hours-long pulses in infrared, and X-rays that rise and fade like a held breath. They may be the signatures of small clumps finally surrendering, or magnetic fields snapping and rearranging, releasing stored energy as heat and light. The overall diet remains sparse, but the pulses are reminders. The engine is idling, not stalled. Mass alone is not the whole story. Some of the noisiest quasars are powered by black holes billions of times the sun's mass. Such giants naturally sweep a larger region, drawing in prodigious fuel. Yet there are also centers no more massive than Sagittarius A times that glow far brighter because their neighborhoods are crowded and chaotic. Environment sets the menu. A dense stream of gas or an infalling galaxy can turn a whisper into a chorus. In a different Milky Way, one with thicker central clouds or more vigorous inflow, our core might blaze, sending out winds that reshape the bar and bulge, and nudging when and where stars are born. The present hush brings a scientific kindness. With the stage lights low, subtler cues come forward. Astronomers can resolve and track individual stars near the core, measuring positions with exquisite accuracy. Tiny variations in their brightness and speed become legible, letting gravity's handwriting be compared line by line with theory. The dim surroundings also make it easier to see small changes in the black hole's own glow tremors that hint at how weakly fed accretion flows arrange themselves when fuel is scarce. Even in a lean time, there is always some signal. Radio waves seep outward from hot, sparse plasma spiraling in. Occasional infrared and X-ray flares add brief accents. Those flashes are windows into the inner few light minutes, where magnetic fields, turbulence, and gas at tens of millions of degrees play out in extreme conditions. The strangeness here is not in the violence that's expected near any horizon, but in the restraint. A predator that mostly dozes feels paradoxical until you remember that galaxies measure their days in millions of years. A nap at this scale can last longer than human history. There is a quiet benefit to such a nap. A violently active center can alter the chemistry of interstellar clouds and bathe wide regions in harsh radiation. Planets near the galactic core would be most affected. Atmospheres can be thinned, surfaces changed. Earth orbits far out on a gentle arm, so the danger would be muted even in a bright phase. But across the Milky Way, the overall climate for life is softened when the core is calm. It's a small, statistical mercy. Fewer storms from the city's center make the outer neighborhoods easier places to settle. As for tomorrow, it depends on what arrives. The central stars mostly keep to stable paths that do not collide with the horizon. Gas drifts in lanes governed by magnetic fields and gravity, sometimes passing close, often passing by. Over long times, orbits precess, clusters pass through, and chance events pile up. A dense cloud might take the wrong turn. A binary star might wander close enough that one member is flung outward while the other is captured and shredded. Any of those could brighten the center for weeks or years. A few years ago, a cloud known as G2 approached on a plunging path that stirred expectations. Would the center flare dramatically when it skimmed past? When the rendezvous came, the show was gentle. The cloud stretched like taffy and some of its outer layers heated, but the great brightening many anticipated did not arrive. The outcome taught a modest lesson. Not every close pass ends at the table. Alignment, density, magnetic structure, many details decide which bits fall in and which go on their way. Next time could be different. A larger reservoir of gas, a stream aligned just so, or a disrupted star could deliver a genuine feast. In such a spell, Sagittarius A times could shine hundreds or thousands of times more brightly than it does now. The radiation would still be softened by distance and dust by the time it reached us, but the galactic center would take on a new prominence, a brighter ember in the constellations of summer. Another path to plenty lies in encounters on a grander scale. The Milky Way and Andromeda are drifting toward each other, and in a few billion years, they'll fold together. Stars will mostly miss direct collisions, but the gas will not be so shy. Tides will channel it inward, swelling the supply at the merged center. The black holes will spiral together, shedding energy in gravitational waves and eventually merging. Before and after, the shared core could flare into true quasar brightness, launching winds that carve cavities in the gas and shift the balance from star birth to star rest in broad swaths. Across the observable universe, snapshots reveal centers in many moods. Some are blazing, some are banked, and many flip between these states across their lifetimes. The cycles are not rhythmic in any human sense. They follow supply lines and accidents, collisions, and quiet spells. On such scales, 1,000,000 years is a long afternoon. It's entirely plausible that our center will murmur along like this for another few million, then brighten, then rest again. There are wilder possibilities. An intermediate mass black hole could meander inward from a captured dwarf galaxy and merge, shaking the region and releasing an enormous pulse of energy. A dense star cluster could be disrupted, feeding the core a sudden cascade of gas and stellar debris. None of this is likely on human timescales, but the universe is patient. It keeps the ledger open and adds to it slowly. Patience, too, shapes what we learn. The present calm lets instruments test ideas that would be hard to try in a glare. Subtle time lags between radio and infrared changes hint at how matter spirals inward. Small differences in polarization trace magnetic fields threading the flow. The dim average makes it easier to tell when a true flare begins and ends. and to weigh how much material might have fallen in during the event. Each small measurement is a stitch. Over years, the stitches hold together into something like a fabric. That fabric wraps around a simple truth. Activity is appetite plus opportunity. Sagittarius A times has the appetite. Opportunity arrives in fits and starts. For now, the pantry delivers small snacks, enough to keep the machinery warm, and the observers hopeful, not enough to light the city from the center. If you stand far out on an arm and look inward on a clear night, what you see is not the engine itself, but the city it steadies. The band of the Milky Way remains a long breath of faint light. The core glows softly, and behind that glow, gravity waits. And then, without much warning, the quiet can be punctuated. A low, even background will suddenly lift. A compact region near the heart brightens, holds for an hour or two, and recedes to its old hush. To human eyes, the change would be invisible. To tuned instruments, it is unmistakable. A brief spark from very near the edge. A small confession from a place that usually keeps its counsel. Every so often, the soft glow around our galaxy's center lifts as if a hand turns a dimmer switch, and for a brief spell, the darkness brightens from within. These bursts, astronomers call them flares, arrive without ceremony or schedule. 1 hour, the region near Sagittarius A times seems as calm as a sleeping lake. The next, it ripples with sudden light, then settles again. The changes are swift and striking, not fireworks across the whole sky, but quick, concentrated flashes that say something near the edge has stirred. Sometimes the brightness climbs dozens of times above its usual level and then glides back down in a matter of hours. There is no calendar for them, no reliable warning. Dust in the foreground keeps ordinary sight at bay, so catching a flare feels like glimpsing a lighthouse beam through fog. You must be looking at exactly the right moment. When a sharp brightening is reported, observatories coordinate like a trained ensemble. Radio dishes tune in, infrared eyes open wider, and X-ray telescopes lean their attention toward the core to collect every photon before the pulse fades. The first time these events were recognized for what they were, surprise had 2 flavors: intensity and speed. The rise and fall were so quick that the emitting region had to be small, no larger than the distance light can travel in minutes. That points to the immediate neighborhood of the event horizon, a place where time and space are steep and matter is sparse. Something close to the edge was speaking up. The question was, which voice? One gentle explanation is ordinary material in extraordinary circumstances. Most of the time, the gas near Sagittarius A times is thin as a whisper, not dense enough to shine much. But clumps exist, shreds from stellar winds, crumbs from dusty clouds, bits from a star that has shed outer layers. If one of those clumps drifts inward and plunges toward the center, friction and compression can heat it to millions of degrees. For a short time, it radiates across the spectrum. Then, if it crosses the narrow threshold, its light ends and its story becomes part of the mass. A flash like that would be brief, hot, and localized exactly the sort of flare observers see. Another path to sudden light threads through magnetism. Near a black hole, magnetic field lines are dragged, twisted, and braided by moving plasma. Energy accumulates in those tangles like tension in a wound spring. When the lines snap and reconnect, an event known from the sun's own flares, stored energy pours into nearby particles. Electrons and ions are hurled to high speeds, and for a few moments the region shines harder in X-rays and infrared before the field resettles. In that picture, a flare is not a gulp of matter so much as a release of pent-up magnetic energy, a rearrangement in the invisible scaffolding that guides the flow. There is also a more dramatic route: encounters with passing bodies, a star, a tight cluster, even a smaller black hole can wander close enough to feel the core's sharp tides. Material can be stripped and spray inward, or an entire object can be drawn out into a long, thin ribbon, a tidal disruption. Most of these events are rare on human timescales, but the center's crowding makes near misses common enough that a few crumbs sometimes fall. Any of these scenarios can produce a short, bright flare. The variety we see, the different colors, durations, and strengths, suggests that more than one mechanism takes its turn. When a flare begins, the best strategy is to listen in many voices at once. Radio traces the slower, larger-scale structures and the cooler plasma farther out. Infrared shows heat from very near the edge, where gas glows as it rushes. X-rays reveal the highest energies, often peaking when electrons are boosted by magnetic fields to near light speeds. Curiously, the flares tend to show up more often in infrared and X-rays than in visible light. That makes sense. The hotter and more extreme the environment, the more the energy slides to shorter wavelengths our eyes cannot see. Yet, even with that rule of thumb, no simple pattern holds every time. Some flares are infrared loud and X-ray quiet. Others reverse the balance. Some are over in minutes. Others linger through an evening. The sky near a horizon is not a metronome. It is weather-structured, but not strictly periodic. A bright episode in 2019 still glows in memory. For a short time, Sagittarius A times shone more intensely than ever recorded, more than twice the previous peak. The spike raised the possibility of something dramatic, a star torn or a cloud swallowed. Follow-up measurements favored a simpler story. A dense lump of gas likely fell inward and burned hot on the way, perhaps a leftover strand from G2, the slow, stretched cloud that had brushed the core in the years prior. Whatever its exact origin, the event reminded everyone that even a quiet center keeps the capacity for sudden emphasis. If this can happen now, in a calm season, then earlier, more active eras must have been rich with light. Indeed, X-ray echoes reflected off nearby molecular clouds hint that centuries ago, the core may have flared hundreds of thousands of times brighter than it does today, like thunder, heard long after the lightning has passed. Close to a horizon, the stage is crowded with forces that, from far away, feel theoretical. Gravity shapes the land, but magnetism shapes the traffic. Field lines thread the plasma and, in doing so, give it lanes and fences, shortcuts and bottlenecks. For years, magnetism near a black hole was treated as background, a useful influence secondary to gravity's rule. Evidence has nudged that view toward a richer balance. The plasma carries its own fields. As material orbits, the fields twist and kink, storing energy, steering particles, sometimes standing as barriers that keep gas from plunging straight in. Then the barriers rearrange, and a fraction of the stored energy flashes outward as a flare. The system is not just falling, it is thinking in wires. A window into that wiring opened wider when the Event Horizon Telescope began to read polarized light from around black holes. Polarization is a subtle preference in the direction light waves wiggle. Magnetic fields can impose that preference when charged particles move through them. By mapping the polarization pattern in the faint ring around a black hole, astronomers can infer how the fields are arranged. Around Sagittarius A asterisk, those patterns trace spirals and arcs, evidence that the fields are strong enough to shepherd plasma rather than drift passively within it. Gravity pulls inward, magnetic tension resists and redirects, and the result is a controlled trickle instead of a roar. The very feature that keeps the center quiet may also be the spring that sometimes snaps and lights it up. Beneath these patterns lies a simple, stark boundary, the event horizon. One way to name it is by the Schwarzschild radius, the distance from the center at which outward paths cease to exist. Compress enough mass into a small enough sphere, and geometry makes a promise it cannot break. Cross this line, and every future is inward. The idea dates to 1916, when Karl Schwarzschild solved Einstein's new equations for the shape of space-time around a perfectly round, non-spinning mass. For a body with the sun's mass, that radius is about 2.95 kilometers. For Sagittarius A times about 4 million suns, multiply that by 4 million, a little under 12 million kilometers, or roughly 7.5 million miles. In human terms, it's vast. In cosmic terms, it's small, only a few dozen times the sun's diameter, cupped in the galaxy's crowded heart. Nothing about that boundary is solid. There is no surface to strike, no crust to touch. The horizon is the place where escape routes end. From far away, it is a mathematical contour you could approach and orbit. Closer in, space itself seems to flow inward like a waterfall, and clocks disagree about how time passes. For an infalling traveler, crossing the horizon would not feel like a cliff. Local physics would behave as usual. To distant eyes, however, the traveler's light would stretch redder and fainter, and the last moments would appear to slow and freeze, never quite arriving, a trick of perspective in a space where time is bent. Images from the Event Horizon Telescope transform such abstractions into something you can picture. At millimeter wavelengths, where dust is kinder, the EHT stitched together a planet-sized array of radio dishes and reconstructed a view, a roundish ring of light with a darker interior, like an embered halo with a shadow at its heart. The darkness is not the black hole itself, but the shadow, a silhouette carved by light that is bent around the hole and captured by it. The true horizon sits just inside the ring's inner edge. From Earth, the whole structure subtends an angle smaller than a donut resting on the moon would seem to the naked eye. Resolving that required the cooperation of observatories from the Atacama to the South Pole, precise atomic clocks to sync their recordings, and supercomputers to weave the data into a coherent picture. Inside the horizon lies a domain that our instruments cannot reach. Equations point to a singularity, a place where density and curvature gallop off the page. Whether nature permits such literal infinities is an open question. Quantum effects likely soften or transform that core on some scale we have yet to measure, perhaps smearing the singularity into something finite, perhaps replacing it with a new kind of structure. Those possibilities are ideas to be tested, not banners to be waved, because the rule that defines the horizon is unforgiving. No signal can escape to tell us. Cause and effect inside are sealed from cause and effect outside. We read the edges and infer the center, the way you read a tree by its bark when the trunk is hidden. The path to seeing even that much of Sagittarius A times was long and layered. In the 1,980 seconds, radio observatories like the Very Large Array in New Mexico refined the view, mapping the central source's compactness and variability. The signal waxed and waned, not wildly, but enough to say the region was dynamic. The next improvement was not a new dish, but a new way to link many dishes into one, very long baseline interferometry. In the 1,990 seconds, telescopes, separated by continents, began to act together, their recordings aligned by timestamps so precise you could stitch waves as if they were measured by a single, Earth-sized instrument. Resolution sharpened until Sagittarius A times measured in tens of micro-arc-seconds on the sky angles, so small that a coin on the moon would be a challenge by comparison. Above the turbulence of air, space observatories added their clean signatures. NASA's Chandra X-ray Observatory, launched in 1999, reported that Sagittarius A times sometimes flared in X-rays, proof that high-energy processes still spark near the core. The Spitzer Space Telescope traced warm dust and crowded star fields in infrared with an ease the ground could never match, slipping past wavelengths the atmosphere tends to swallow. With each instrument, the puzzle lost a little of its fog. Sub-millimeter light, the interval between radio and infrared, brought another set of tools. The sub-millimeter array on Mauna Kea and ALMA on the Chajnantor Plateau in Chile, both perched at altitudes where the air is dry and thin, began to read emission from material very close to the black hole. At those wavelengths, astronomers could watch the base of flows and the whisper of hot, tenuous plasma. Arrays matter here because resolution needs distance. By spreading many antennas across a wide plane and combining them, you gain the sharpness of a much larger dish. All these threads converged on an audacious goal: to image a black hole's shadow directly. Doing that meant pushing VLBI to the limit, synchronizing observatories across half the planet, and insisting that the sky cooperate for precious, shared nights. By the 2010 seconds, the Event Horizon Telescope had woven its network, ALMA and APEX in the Atacama, the Sub-Millimeter Telescope in Arizona, the Large Millimeter Telescope in Mexico, the SMA and JCMT in Hawaii, the IRAM dishes in Spain and France, the South Pole Telescope at the end of the world. They tuned to 1.3 millimeters, a wavelength short enough for fine detail and long enough to sneak through dust. Sagittarius A times posed a particular challenge even then. Unlike the supermassive black hole in M87, which presents a relatively steady silhouette, our center changes on timescales of minutes. Hotspots orbit quickly. The brightness shifts while the network is still collecting data. Imaging it required algorithms that could handle a moving target, reconstructing not a single still scene but a kind of averaged portrait of a restless ring. The reward was the first tangible outline of the boundary that had been a formula for a century. A dim center carved from light by gravity itself, surrounded by a soft, uneven collar where radiation from infalling plasma curves piles up and escapes. Folded into that portrait was polarized light, the quiet signature of magnetic fields shaping the glow. The patterns were not smooth circles. They were swirls, hints that the plasma near the edge is threaded by organized fields, capable of guiding matter and storing energy. Those same fields likely help set the trickle that keeps Sagittarius A times subdued most days, and may also prime the brief, bright flares that punctuate the calm. Between gravity's pull and magnetism's weave, the center chooses its pace. None of this replaces the old, quiet choreography of stars. It completes it. On one scale, orbits tell you how much mass sits in the center and how tightly it is packed. On another, polarized rings tell you how matter behaves in the last few light minutes before the fall. Between them lies the everyday hum radio murmurs, infrared embers, occasional X-ray sparks that let us watch the core idle, twitch, or briefly awaken. Put together, the picture is not of a monster forever roaring, but of an engine with a patient idle and a temper that shows in flashes. A city's center at night, mostly lamplight, and motion in the streets, punctuated now and then by a sudden, brilliant window. What remains for us is to keep the vigil, long nights of listening at many wavelengths, notes compared across continents, and the line between theory and observation tightened a little each season. In that steady attention, the flares become not interruptions but part of the rhythm, short phrases in a longer song. And every time the brightness needle jumps and settles, we are reminded that even a quiet heart has its voice, and that near the horizon, where time leans and light bends, brief moments can say as much as years. In 2017, the Event Horizon Telescope turned its full attention inward, asking the planet to behave like a single, steady eye and watch Sagittarius A times together. The observing nights were coordinated like a heartbeat. Hawaii at dusk, the Atacama at midnight air, the South Pole wrapped in its own deep cold, each dish recording waves with time stamped by atomic clocks, each site filling a different piece of the Earth-sized lens. The real work blossomed only after the shutters, in a sense, closed. Petabytes of raw signals, vast whisper-thin patterns of interference, were flown to twin data centers, where teams began the slow, careful work of aligning and calibrating every thread. Each telescope had seen the same scene from a slightly different angle, through slightly different weather, with electronics that had their own personalities. To rebuild a picture, the timestamps had to line up to billionths of a second. The amplitudes had to be scaled. The phases, those delicate measures of where a wave's peak falls, had to be reconciled. Unlike a photograph, no single exposure could be developed. There were gaps in the virtual aperture places on the Earth where no antenna stood, so the Fourier plane had holes. Algorithms became brushes. Some favored smoothness, some preferred compact features. All were trained to distrust wishful thinking. To keep bias at bay, the collaboration divided into independent imaging groups that worked in seclusion, like jurors deliberating separately. When the walls finally came down and the reconstructions were compared, the outlines agreed in the ways that matter: a ring, a shadow, a size that matched gravity's prediction. The first public unveiling of a black hole's shadow came not from our own center but from a giant far away. In 2019, the collaboration showed the world M87*, a blurry ember ring around a dark interior, a silhouette carved by gravity from light. M87's mass, about 6.5 billion suns, made its horizon large in angular size, despite its distance, and its inner flow evolves lazily by comparison, changing over hours to days rather than minutes. That steadiness let the network collect a cleaner set of snapshots before the scene shifted. The image felt like a hand placed softly on Einstein's shoulder. Your equations work even here. Sagittarius A times was always the subtler task. The target on the sky is tiny, about the apparent size of a donut on the moon, so every error is magnified. More challenging still, its brightness pattern changes on human timescales. Hot spots whirl near light speed, close to the edge, and the glow rearranges itself in minutes. If you try to combine hours of data as if the scene were frozen, the result smears like a candle flame in a gust. Classic radio interferometry wants the source to sit still. Sagittarius A times politely refuses. To meet a quick target, the team rethought the choreography. Rather than insist on a single, static portrait, they generated thousands of images, each consistent with the data, but seeded with different assumptions, then looked for features that survived across the ensemble. They also built methods that seek patterns in time, not a still life, but a kind of averaged motion, a portrait drawn from frames that never quite hold still. GRMHD simulations, numerical weather reports for magnetized plasma in curved space-time, served as reality checks, guarding against mistaking algorithmic preferences for nature. Out of that patient accumulation emerged the familiar, yet fuzzier ring, a dim center surrounded by a glow, roughly the size general relativity predicts for a 4 million solar mass hole at our distance, but jittery, as expected for a restless source. The public saw that image in 2022, a sibling to M87 asterisk silhouette with a more mercurial temperament. A picture, even a historic one, is a beginning more than an end. What the ring confirms: mass scale, the presence of a shadow, the basic geometry of bending light, was long anticipated. What it does not yet tell plainly are the details that give a black hole texture, how fast it spins, exactly how its axis tilts toward us, how magnetism and turbulence set the rhythm of inflow and outflow. Spin especially matters. A rotating black hole drags space-time around with it, a phenomenon called frame dragging, which changes the innermost stable orbits, sculpts the flow, and when circumstances allow, helps collimate jets. In M87 asterisk, a luminous jet points like an arrow, suggesting an axis and hinting at rapid rotation. In our center, no grand jet announces direction. If outflows exist, they are small and easily masked by the crowded, dusty foreground. Orientation and spin hide in subtler signatures. One route to those signatures is to read the alignment of light waves themselves. Light doesn't simply carry energy, it carries a preferred wiggle. Scattering, magnetic fields, and curved space can all imprint a pattern on that wiggle polarization that survives the journey. Near a horizon, X-ray photons are born in hot, thin plasma, and then hurled through a labyrinth of gravity and magnetism before escaping. A spinning hole twists the very coordinates through which they move. Measure the polarization well enough, and you can back out the geometry, the tilt of the flow, the strength and order of the fields, the rate of rotation that best explains the imprint. That is the promise behind X-ray polarimetry. NASA's Imaging X-ray Polarimetry Explorer, launched in late 2021, was built to make such measurements with a gentleness and precision earlier missions lacked. Sagittarius A times is a faint X-ray source most days, but during flares its voice grows strong enough to try. Catch a bright event with IXPE's detectors, and the angle and degree of polarization become clues how much ordered field is present. whether the electric vectors swirl as frame dragging would suggest, whether the photon's last scatterings happened in a plane aligned with a disk or in a puffier, more spherical flow. It's a delicate kind of seismology for light. Meanwhile, the millimeter wave polarization mapped by the Event Horizon Telescope offers a complementary view. At those wavelengths, synchrotron radiation from electrons in magnetic fields dominates, and the polarization pattern across the ring sketches the field structure. Around Sagittarius A*, those patterns suggest fields that are organized enough to steer plasma and store energy, yet flexible enough to rearrange and release it, consistent with the flares that punctuate the calm. Put together, X-ray and millimeter polarimetry promise a stereoscopic sense of the inner region. Hot, high-energy processes in one eye, cooler, structural guides in the other. The practicalities that led to the 2022 image are their own quiet triumph. The collaboration learned to handle a source that won't sit still, developing movie-aware imaging that respects time as well as space, using closure quantities, phase and amplitude combinations, immune to certain calibration errors, to anchor reconstructions, and leaning on independent pipelines to keep enthusiasm from driving the shape. They learned to police their priors, testing whether rings appear even when the data do not demand them, and to discard anything that seemed to be algorithmic wish fulfillment. They learned to fold atmospheric and instrumental quirks into their uncertainties so that the final product wore its honesty on its face. The differences between M87 times and Sagittarius A times remain useful guides. One offers a slow, stately glow and a visible jet. The other, a quickening ring and no clear arrow. One is so massive that its inner flow evolves over many hours. The other changes in minutes. Yet the shared silhouette tells a soothing story. The same geometry governs both, a ring size set by gravity's curvature, a shadow that is not a metaphor, but a measurable deficit of light, where photon paths and horizons conspire. Across scale and temperament, the underlying rules hold. Behind the public images, a quieter stream of results continues. Astrometry of the ring centroid as the brightness shifts can reveal a preferred direction and axis hiding in wander. Correlations between infrared and millimeter variability hint at how disturbances propagate inward, cooling and expanding as they pass. Comparisons between polarized patterns on different days weigh the balance between ordered and tangled fields. Each of these measurements trims away possibilities. A disk tilted too far would predict a polarization signature we do not see. A spin too slow would fail to explain the inner brightness distribution. A flow too thick would smear out the short timescale flickers that are observed. Some of the most evocative ideas are also the most cautious. Hotspots, temporary clumps in the flow, could orbit close to the edge, their motion modulating the light in a way that, with enough signal, would trace the space-time metric directly. Lense-thering precession, the slow nodding of orbits in a dragged frame, could imprint a low-frequency rhythm on the variability. If those patterns can be isolated from the general weather of turbulence, they become rulers laid against the geometry, letting observers read off spin and inclination with fewer model assumptions. The path forward is not only algorithmic, it is architectural. Add more stations to the EHT's network, Greenland, Africa, additional dishes in the southern hemisphere, and the holes in the virtual aperture fill. Observe at multiple frequencies close together, and you learn how optical depth changes across the ring, separating emission that originates nearer the horizon from emission that arises farther out, pushed to shorter wavelengths, where the scattering from intervening dust is gentler and fine detail sharpens. Eventually, repeat observations across many years will allow not just averaged portraits, but true time-resolved movies, images that track structures as they move and fade. None of this erases the simple, quiet satisfaction that came with the first ring. It adds layers to it. The 2019 image of M 87 times was a door opening. The 2022 image of Sagittarius A times was a second door, more delicate, showing that the doorway itself was no trick. Spin and tilt still ask their questions. Magnetic fields still tangle and untangle in ways we are learning to map. X-ray flares still arrive without appointment, offering brief moments when the inner geometry writes a clearer signature. Each new technique is a candle held up to the same room from a different corner. Beneath the machinery is the same night-friendly truth that has guided this whole story. Steady attention changes what is visible. A network of dishes separated by oceans learns to think as one. Petabytes of phase and amplitude acquire the weight of a picture. A fuzzier ring becomes a clock for gravity, and its polarization a weather vane for invisible fields. Spin will come into focus as measurements accumulate. Orientation will sharpen as patterns repeat, and the choreography at the edge will trade a little of its mystery for the dignity of being understood. For now, that ring is a promise. It tells us that space curves the way equations said it would, that light behaves as if guided by those curves, and that even in a place where time leans hard, we can still take its measure. It tells us that a small, quick target can be seen honestly if you respect its motion, and that disagreement between methods is a feature to be resolved, not a crisis to be feared. It tells us that the center of the Milky Way is not only a mass to be weighed, but a workshop where gravity, magnetism, and motion make a living, and it leaves room for the next bright flare, the next polarization map, the next season when the whole Earth listens again, and the glow at the heart of our galaxy answers in rings and whispers. Looking ahead, the Earth-sized ear we've built will only grow more attentive. Each new dish added to the Event Horizon Telescope is another stitch in the planet-wide lens, another way to fill the bare patches where the music used to leak through. Plans whisper about silent summits in Africa, quiet Pacific islands, and more daring still antennas lifted into orbit to look down with the cold patience of space. When orbiting radio eyes join hands with mountaintop observatories, resolution sharpens in a way that turns still frames into something closer to a time-lapse. Bright knots circling the brink, filaments forming and unspooling, a candle's flame drawn slow enough that the eddies show. New receivers will listen at several wavelengths at once, so temperature, density, and motion stop being guesses and instead arrive as layered clues, each color of radio light telling a part of the same story near the edge. Another sense is coming into its own, the one that doesn't need light at all. Gravitational waves are ripples in space-time itself, the fabric shifting a hair's breadth when massive things hurry or fall. A steady, quiet giant like Sagittarius A times barely stirs that sea when it's alone. The curvature around it is deep, but not changing quickly. To raise a ripple loud enough for us to hear, the dance has to grow dramatic. A smaller black hole spiraling in, a dense star dragged close and torn, or two supermassive black holes embracing and becoming one. Ground-based detectors have already heard the quick, high notes of stellar mass collisions, the lower, slower tones, Notes that take minutes to hum a single cycle belong to space-based observatories that float far from Earth's noisy ground. One of the most promising melodies has a name that sounds technical but feels simple once you sit with it: an extreme mass ratio in spiral. Picture a compact traveler, a neutron star, or a black hole, only a few dozen suns, heavy caught by Sagittarius A times and settling into tighter loops over ages. Each pass steals a little energy, and the path shrinks. As the traveler approaches the inner orbits, the wave it raises deepens and clarifies, like a cello string tightened, a turn at a time. In the final months or years, right before the plunge, the signal becomes unmistakable, slow to human ears, rich in information. It's far too low in pitch for the ground-based instruments tuned to faster crashes, but it sits in exactly the range a fleet of spacecraft can hear. That is the point of LISA, the Laser Interferometer Space Antenna. 3 spacecraft flying in a triangle, millions of kilometers wide, measuring distance changes smaller than an atom as a wave passes through. If a small object ever spirals into Sagittarius A times while LISA is listening, the reward will be precise in a way that light alone cannot match. Mass and spin could be read with surgeon's calm. The geometry of the last stable orbits, the way space-time twists around a rotating hole, the frame dragging that makes a compass lean, all of it would announce itself in the rhythm of the wave. If the pattern strayed even slightly from Einstein's prediction, that deviation would be a doorway. New physics hinted not with a bang, but with a measured, repeated note. Waves carry one advantage that light never earns: indifference. Dust cannot scatter them. Magnetic fields cannot turn them aside. They arrive bearing news from just outside the horizon, from places where photons struggle and plasma confuses. In principle, they could let us feel the space right next to the line we can never cross, the shoreline of the unseeable sea. And they are not the only promised news. Far in the future, another story waits, one that involves not a single center but 2. The Milky Way and Andromeda are not strangers. They have been walking toward each other all along. The pace, about 110 kilometers per second, feels leisurely by cosmic standards, relentless by ours. In roughly 4 billion years, the 2 disks will begin to interleave, tides pulling gas inward while stars, mostly, miss each other and glide through. Where gas meets gas, traffic jams form. Clouds collapse. The cores brighten. Each galaxy's central black hole drinks more deeply for a time. The night sky, for any witness who could bear that long view, would slowly recompose itself. Andromeda swelling, lanes of dust like brushstrokes, curtains of young stars lighting up and fading again as the cycles run. Spiral order does not survive such a meeting. The neat arms give way to a more rounded body. Orbits that were once calm and almost circular become a library of directions. Some stars are flung outward into the black between galaxies, set free to wander for eons. In the middle, Sagittarius A times and Andromeda's central black hole notice each other's pull and begin a slow, stately, tightening wide loops, becoming smaller ones as gravitational waves take their tax each pass. This courtship lasts tens of millions of years, speed rising, separation falling, the waves growing louder and lower until the horizons meet and meld. The merged core will be heavier by many millions of suns, and its spin will carry the history of both parents, a composite of their rotations and the direction of their last dance. For life, if life persists anywhere by then, the consequences depend on address. Close to the center, The radiance from infalling matter could scour atmospheres or change chemistry. Farther out, where most stars end up, the changes are gentler and stranger. Constellations you once knew erased and replaced. Sky maps that no longer agree on names. A gradual loss of the spiral's elegant geometry. Even to ask who might be around to see it is to feel the scale of these plans. 4 billion years is the time between the first stirrings of life on Earth and us. Long before the Great Meeting, the sun will grow kinder to no one, brightening enough in 1 billion or 2 to make oceans thin, water escape, the air lose its softness. 5 billion years from now, it will swell into a red giant. Earth may be consumed, or it may bake to silence and ash. In either case, the surface that holds our stories will not be a place to sit and watch. Perhaps some descendants, ours or someone else's, will have found other shores, other suns. Perhaps there will be minds in places where night still falls and skies can be red. Perhaps there will be no need for skies at all. There is a slimmer possibility that Earth survives in a stable path, misses the worst of the heat, and drifts through the merger as a relic under a fading star. In that rare world, Andromeda would bloom into a haze that grows by slow degrees, dark lanes crossing light like charcoal over milk. A person patient enough could watch whole tapestries of star birth sweep across the vault. When the two cores come close, the merged center would brighten like a far hearth. All of it would unfold like a celebration that never needs to end, an event that lasts longer than memory. This long view doesn't diminish the quieter work here and now. It deepens it. From the first accidental radio hiss heard by an engineer trying to clean up transatlantic calls, to the ring we piece together by making the whole Earth into a lens, the path to Sagittarius A times has been a curve traced with small steps. We watched nearby stars veer in their courses and weighed the mass, pulling them without ever seeing the hand. We measured the bending of time and the color of light in a gravity well, and found them as dependable as the equation said. We made a picture of a shadow by listening for light that had almost escaped and then turned back. Yet the drawing is still unfinished in ways that matter. The exact spin keeps its number. The feeding habits remain fussy and changeable. The next big flare refuses to be scheduled, like weather that insists on being weather. Upgrades are already answering that stubbornness with craft. The EHT's network will add stations where the aperture has holes, so the next season's reconstructions lean less on assumptions and more on direct coverage. Receivers that can observe 2 or 3 close frequencies at once will let us see which parts of the ring are optically thin and which are thick, which layers of the flow we're looking through and which we can look into. Polarimetry will keep tracing magnetic fields on the sky like grain in wood, so we can say not only that the field is there, but how organized it is and where it stores energy before a flare. Simulations that include both magnetism and relativity will be tuned by data until they stop being sketches and start being tools, a way to predict which patterns should repeat and which should never appear at all. Gravitational wave observatories in space will add a sense we've never had at these scales, letting us listen as well as watch when small companions spiral in. When that happens, mass and spin will be measured 2 ways, once by light bent in a ring, once by ripples carried across a vacuum. Agreement will be a comfort, disagreement will be a beginning. Either way, the center of the Milky Way becomes not just a weight to be estimated, but a laboratory, a place where gravity can be tested, not in chalk on a board, but in the sky itself. The beauty in all this is how familiar it starts to feel once you spend time with it. The heart of our galaxy is not a perpetual fireworks show. It's an old square in a city, full of small currents and quiet motions, a gravity that steadies the place without demanding attention. Presence shows up as what it asks others to do. Orbits bend a little, light reddens a little, dust warms a little. And once in a while, a window flares bright for an hour, and you learn something new about the building it's in. That, too, is a kind of kindness, the universe choosing legibility over spectacle, often enough that patience has somewhere to sit. We don't need to know everything to feel the shape of what's true. Space-time curves the way the field equations promised. Light threads those curves with loyalty. Gravity can be both fierce and quiet, an anchor, not a storm. The blank places on our maps are not voids. They are invitations to slow down and add another instrument, another way of listening. Sagittarius A times is not a period at the center of a sentence. It's an ellipsis. The rest of the line is ours to write. A new dish set on a dry peak, a laser reading a change smaller than dust, a million wave fronts stitched with the care of a quilt. If, in the hush of night, all this feels close rather than abstract, that's because the rules at the edge are not so alien after all. The ring we drew is a pulse you can read, like a heartbeat, steady in its average, variable in its detail, honest in its limits. Against that constancy, each new method adds a note. EHT upgrades refine the outline. Millimeter polarimetry reveals the grain. X-ray polarimetry listens for the twist of frame dragging. Liza, when it flies, will bring the low notes that pass through everything untouched. Together, they turn a single subject into harmony. So, the promise is simple. When we ask more carefully, the center answers more clearly. The next season of Coordinated Nights will likely bring a ring a little sharper, a pattern in the variability a little less shy. The next bright flare will arrive without permission and leave a measurement we couldn't make before. The next map of polarization will show how the invisible scaffolding has changed since the last. And someday, in a different sky, a different instrument will feel the slow swell of a small companion's fall and tell us how fast the big heart turns. Until then, the galaxy's core keeps its quiet job. It doesn't require our understanding to hold the stars together. It doesn't need our attention to do its work. But when we do pay attention, when we lend it our careful ears and steady eyes, it gives back something rare. The sense that the universe, however strange, is trustworthy. Not tame, not safe, but lawful in a way that lets projects, friendships, and promises take root even under an alien sky. That trust is the soil where meaning grows. Rest with that for a moment. Picture a thin, embered ring far away, light bending around a dark that is not emptiness, but a boundary the world respects. Picture bright knots that orbit and fade, and the faint, ordered wiggle of light that betrays a magnetic field you will never touch. Picture quietly the future triangle of satellites, measuring a change in distance smaller than an atom because a wave from the center passed by. None of these are loud. All of them are true enough to sleep on. And if tonight the galaxy feels closer, let it. The heart of the Milky Way is holding steady. When the Earth gathers its eyes again, it will answer in the same language, rings and whispers, flares and pauses, a grammar of light and gravity that keeps offering new lines to read. Where we stop is not an ending. It's where a long breath turns and the next breath begins. So let that breath linger. Let your shoulders settle into the mattress, the way starlight settles into a long exposure quietly, without hurry. If the mind wants a final image to hold, keep the embered ring and the calm machinery behind it. Clocks humming in distant domes, dishes listening across oceans, a patient chorus translating whispers into something we can trust. We don't have to own the whole picture to rest inside it, knowing that the center keeps its rhythm and that we've learned how to listen can be enough for tonight. If a thought drifts back in, let it be a simple one. The universe is strange, but it is also consistent. Gravity doesn't bargain. Light doesn't lie when it bends. Numbers taken carefully tend to agree. That's a kind of kindness, really, a steady floor under our smaller uncertainties. Out there, bright knots will circle and fade. Fields will twist and relax. Somewhere, a brief flare will lift and fall. In here, your breath can match the pace. In for the gathering, out for the release. Tomorrow, more instruments will wake. More data will fold into place. More models will be sanded smooth against the grain of what is. Maybe a new flare will arrive. Maybe a quiet night will pass and teach us just as much. Either way, the center will answer in its old language and will add another line to the margin of our map. For now, let the map close. Let the room dim to its natural dark. Imagine the Milky Way like a city after midnight. Avenues of stars breathing slow, the deep keel at its heart holding course. You don't have to hold it in mind. It will hold itself. And as the last wakeful thoughts soften rings and whispers, flares and pauses leave them to drift where the numbers go when the telescopes sleep. The sky will be there in the morning. So will the rhythm. So will you.